Hello everyone, and welcome to this presentation. My name is Pablo Pérez. I'm a PhD student at Aalto University, and today I'm presenting the work that we submitted to Interspeech 2021 in collaboration with Mariem Bouafif from Manar University, Tom Bäckström from Aalto University, and Zied Lachiri from Manar University. The title of our work is Cancellation of Local Competing Speaker with Near-field Localization for Distributed Ad-Hoc Sensor Networks. So let's get into the context of this project. The reason for this work is to protect the privacy of speakers that are external to a specific conversation or interaction with a voice user interface. The way we propose to do this is by using source separation techniques for crosstalk cancellation when there are multiple devices that can interact in the same scenario. And the final goal of this project is to remove the information from the interfering speakers from the signal received in a specific device, such that only the speech from the user is processed by the application. But why voice user interfaces? Nowadays, voice user interfaces are integrated in almost every electronic device around us, and all of these devices have the ability to record sound, process it, and transmit it. This means that every member in a household has easy access to at least one device providing a voice user interface. With the increased use of voice user interfaces and having to spend more time inside our homes, it is very likely that multiple people use their voice user interfaces simultaneously in the same space. And if our voice is captured by another device, which we are not specifically using, that could lead to a violation of our privacy. So let's take a look at a more specific example. We go from a scenario with one speaker in a room to having multiple devices providing voice user interfaces to multiple speakers simultaneously in the same acoustic space. Therefore, we don't have anymore only a direct speech signal to our device, but we need to consider the added interference captured by our microphone from other speakers. If a user's voice is captured and processed by a device he didn't agree on using, that would entail a violation of the user's privacy. What we propose then to solve this problem is crosstalk cancellation. Imagine that we have two devices in the same acoustic space that can communicate with each other. Each of them are simultaneously recording the signal from their user and the interference coming from the other individual. The resulting mixture contains information from the speech of both users. But if our devices share their recorded signal with each other, they can apply crosstalk cancellation techniques to estimate the initial target signal and remove the interfering information. The method we propose for crosstalk cancellation can be divided into two submodules. First, we have a localization model that will estimate the direction of arrival of the target source. The second module then calculates a time-frequency softmask that will remove the information from the interfering speaker in the mixture. In the first module, we transform both signals into the frequency domain using short-time Fourier transform, and we extract the cross-power spectrum, inter-device level difference, and inter-device time difference, which will be the features analyzed by the model. These features are grouped depending on their frequency, and their different frequency blocks are processed by independent deep neural networks. The output of the network is combined into a probability mask that will be used by the second module to calculate the softmask for crosstalk cancellation. The network of each block can be divided into three steps. First, an initial autoencoder receives an input of 321 samples composed by the features mentioned before, corresponding to that specific frequency block. This autoencoder generates 256 features that are then used by a second autoencoder. The result of the second autoencoder are another 256 samples, taken by a softmax classifier, which estimates the probability distribution of the direction of arrival. This is represented as 19 values corresponding to the possible directions. To train the network, first, we train the first autoencoder on its own. The weights of this autoencoder are then locked, and the second autoencoder is trained with the generated features. Finally, both train autoencoders are locked and we train the softmax classifier. One last round of fine-tuning is performed over all the network once these three parts have been individually trained. Our experimental setup is composed by 2 speakers and 2 microphones. We can define a dominant speaker as the speech that we are trying to extract, and the interfering one as the signal that we want to remove. They both are then located close to their corresponding device. As the distance between the speakers and the microphones is smaller than 3 times the distance between the microphones, we will be working in the near-field context. The microphones are located 1, 1.5 and 2 meters apart from each other, and the speakers will be at random positions at 1, 2 and 3 meters away from the center of the array. The speakers will also cover a range of directions of arrival between -90 and 90 degrees in steps of 10 degrees each. It is important to notice that to consider a scenario as we described before, the dominant speaker will always be closer to the reference device, while the interfering one will always be closer to the secondary device. The speech samples for each speaker are formed by randomly extracted utterances from the LibreSpeech dataset. We divide the evaluation of our method into the 2 parts that compose the proposed model. First of all, we will analyze the accuracy of the DOA estimation by the section of the model dedicated for localization. The figure shows the relationship between the real DOA and the one estimated by the networks. As we can see, there is a high accuracy in the estimation of the DOA values around 0 degrees, and the accuracy of the estimation decreases as we approach the higher angles. This reduction in the quality of the estimation happens because we are closer to the axis of the microphone array. However, the estimation error stays within ±20 degrees, which is still an acceptable value for the application that we propose. The second evaluation method will be the quality of the crosstalk cancellation. In order to evaluate this, we will use 2 metrics: the signal to interference ratio and the signal to distortion ratio. The SIR represents the amount of interference present in our signal, and the SDR shows the degradation of the signal due to the interference removal. Input signals were designed with initial values of 0, 5, and 10 dB of signal to interference ratio, and the 2 figures on the right represent the improvement of these values with respect to the original signal. The results are compared to an expectation maximization blind source separation method that we refer to as MESSL. As we can observe in the SIR figure, the proposed method achieves a higher interference rejection, and we can observe higher performance in the lower DOA values, similarly to the DOA estimation performance. In terms of distortion levels, the performance of our method is similar to the reference for lower DOA values, but there is a higher distortion introduced in the higher DOAs. This is probably caused by the nature of the soft-mask method, which can remove great parts of the interference in exchange for higher distortion in the signal. In conclusion, when multiple speakers talk simultaneously to their devices in the same acoustic environment, the speech from competing speakers will leak into all other devices. This not only reduces the quality of the audio signal, but can lead to violations of the user's privacy. For example, if my voice is captured by another device and used in an application that I haven't specifically approved, that would entail a violation of my privacy. To solve this, we have presented a direction of arrival-based source separation model that can be used for crosstalk cancellation in the near-field context. The model provides a good estimation of the direction of arrival, and the calculated time-frequency mask achieves high interference rejection. However, the removal of the interference also introduces additional distortion into the signal, and therefore it is necessary to find a compromise between interference rejection and signal distortion. In future steps, we are planning to adapt the proposed method to real recordings, which, unfortunately, we couldn't obtain last year due to the difficulty to organize recording sessions. And considering that this method relies on devices communicating the recorded signals to one another, we will analyze the effect of quantization noise that can be introduced by traditional speech codecs like EBS or Opus. This is the end of the presentation, so thank you all for attending, and I will be here to answer your questions.